So this is a slide from last Friday. And one of the things that it illustrates is this idea. It's one view of what happens when encapsulation occurs. So the idea is that you have these nested chunks of digital information. On the, and let's take this in a little closer. So you have a physical layer below this, and that's down here. And what happens in terms of networking on the physical layer is that one type of media, whether it's metal wire or electromagnetic waves, radio waves, wireless and Wi-Fi and cellular, or light pulses in fiber optics, they basically are flowing, signals are flowing across media. So on the physical layer, you have signals flowing across media, and those signals are used to represent bits that are traveling over the physical media. So you have bits over signals and signals over wires. Just to explain in layman's terms what's going on here on the physical layer down on layer 1. And then this is layer 2. So if we're looking at the 5-layer model, layer 1 is not shown here, but I want you to understand. If I pull up an email client and I want to send email to someone else on computer 2, my email application is going to start with a message, an email message, and the technical definition on this layer is called a datagram. It has a header, it has a certain format. Remember the syntax and semantics. Every protocol has syntax and semantics. So there are rules and there's a format. There's a way to understand if the message is complete, and the application passes this down to the transport layer. And because we want to guarantee delivery of the email message, that's different than streaming media for music or video, where you can have a split second that's missing and it doesn't end the world. But if you have part of an email message that's missing, it could end the world, right? So that datagram flows down from layer 5 into layer 4, where TCP gets a hold of it. And TCP has created a session, a formal telecommunications digital exchange, session with a server, the email server. And what happens is that there's this handshake that happens. And again, it's called a datagram at this level, but there's information embedded in that TCP protocol that helps the email server out here on the internet to know, is my email message complete? You want to guarantee delivery, so you have to have a way of guaranteeing that all of the data gets across. When that's finished, all right, so you have this bundle or package of digital information in an email, and it's bundled or packaged in another envelope, or it's encapsulated. It's put in a digital capsule with additional information. And on this layer, the transport layer, when that work is finished, it's passed down to the internet layer or the network layer. And in the OSI 7-layer model, internet is called network. It's got a slightly different name. On the internet level, this is called a packet. So the datagram from the transport layer, which is slightly larger than the datagram here, is basically, hang on a sec. Okay, is everybody with us? Everybody here?
Yeah.
Okay.
Yeah.
Sorry for the delay, the pause, and thank you for your patience. Okay, so we have the email message. It's a datagram. It's a bundle of information. It has a certain format and a certain process where it's worked on by the email application, layer 5. It's passed down to the transport layer where additional information is added so we can tell whether or not the chunks of the email are all making it and if they're making it in the right order so they can be ordered as they get across the other side. A session is formed. A session is formed on the transport layer between this computer and the email server out here on the internet. So what's not shown here is the email server out on the internet. Good afternoon. So you have this datagram that's a little larger now with additional information, and this capsule of additional information was formed. It drops down to layer 3 from layer 4, where it's encapsulated. It's placed within an additional package of digital formatting, right? This time with network addresses. So across the internet, you have to know where to find that email server in order to transfer the email message from the email client, which is an application, out across the physical network to the email server. So there's a client server connection that's occurring here. And you have to know the sending network address and the receiving network address. So the packet, at this point, the datagram is dropped inside this packet, and so the name changes, right? So this bundle of digital information now is even larger, and the packet has to and from addressing, network addressing on it. And at the end of each of these bundles of information is like this packing list we call the CRC. Okay, I did revise, I want to tell you, I went into your study guide and I found the places that were disjointed in terms of the graphics, and I did change some explanation of things. And so I wanted to show you here, when we talk about the IP network address, when we talk about a bundle of information and encapsulation, let's get all the way down here. There. So last Friday we were explaining that as each of these bundles of information are being formed, so here's layer 5, that's the application layer where I was showing you this other view of the email application. So that's this layer here, layer 5. It's called a datagram. It's called a datagram on layer 4, where the TCP protocol establishes a session with the email server, and there's additional formatting and process. There's syntax and semantics to ensure that the entire message gets to the server. In order for that to happen, this datagram is bundled inside another package of digital information, only this time it's called a packet instead of a datagram. There's sending and receiving addresses, and we're going to talk about IP network addresses in a minute. But there's also this packing list at each step of the way. Once this computer says, okay, I'm at, this is from my network address here, it's going to this email server network address there. There's another packing list or packing document that says, okay, if it's all here, this is how many bytes it should be. This is where the message should start. This is where all this stuff. It's passed again down to the layer 2, which is what we call the local area network layer. So this is the internet or wide area network layer, and then this is the local area network or LAN level. The packet is placed within yet another digital package. It's encapsulated, or put inside another digital capsule. That digital capsule includes the MAC, the media access control identity of this computer, and the media access control identity of the network router that receives this frame. So the packet is put inside what's called a frame. It's another term, so it's another clue or cue that, okay, I'm operating on layer 2. If you ever hear frame, layer 2, packet, layer 3, datagram, 4 and higher, right? That frame includes a packing list, and it includes the media access control identity or MAC address of this computer and the network switch that's going to relay this out onto the open internet. So this is global in focus. The addressing and information of the packet is substantial enough and provides all the essentials for a person to guarantee that that digital information is going to get anywhere in the world. This information provides enough information. This information provides what's needed to get the frame to the edge of the local network on the switch so that it can be routed out onto the internet, onto the public internet. So you have this local area network, or what we call the data link layer. So the physical layer is linked to data on the data link layer or network interface layer. Network interface cards are often called NICs, okay? If you draw this out and you say that this is the header for a layer 5 datagram, the email message itself, the CRC portion or the tail of that, it's called a protocol data unit. This whole thing together is called a protocol data unit, or PDU. That's dropped down inside the TCP datagram. It fits precisely down inside here, where yet another header is added with the TCP header information. Another CRC or tail or packing list is added, right? So what you have is a protocol data unit on layer 4, which includes the protocol data unit from layer 5. Now you'll notice inside here we keep talking about the SDU. So I want you to think about the larger containers and how they fit inside and how they fit inside. That whole chunk on this layer is called the PDU, but the payload inside is called the SDU, the service data unit. So what are we saying? Email is a service, and that email message is the service data unit that fits inside the protocol data unit. So the SDU on layer 5 is the email message. When we drop it down inside here, right, the service data unit that's embedded, or the payload that's embedded inside the layer 4 protocol data unit, we would call the TCP datagram. That's the payload or the service data unit. The TCP, actually this whole thing is the TCP data unit. That's the PDU. But what's inside here is the email PDU, right? So what I'm telling you is that if you're dealing with the entire chunk of information on that layer, we call that the PDU, and I want you to know the names. So one of the questions you can anticipate on your assessment is, hey, I have something going on with my protocol layer, and I'm on layer 3. What is the protocol data unit for layer 3? And you're going to say, oh, it's a packet. That whole chunk, that whole envelope, that whole capsule of information on layer 3 is referred to as the layer 3 PDU, and it's called a packet. But if I, in that same question, ask you, okay, so the packet is unloaded. What do I use to make sure that the whole thing got there intact? I use the CRC. And what is that payload called? What is the payload for layer 3 called? Or what is the SDU called? Well, we would call that the TCP datagram. So the TCP datagram up here is the PDU for layer 4, but once it's encapsulated, once it's stuck in the envelope and sealed with a packing list and additional address information, now on layer 3 we have a different PDU, a different protocol data unit. It's called a packet, and what's inside the payload that you can unload and unload, that service data unit is called a TCP datagram. What I want you to understand is that the terminology can get confusing. If I say I'm talking about a TCP datagram, one of your questions should be, okay, I got you. You're talking about a TCP datagram, that's layer 4. Are you talking about it being the payload on layer 3, or are we on layer 4? Right? Because if we're on layer 3 talking about a TCP datagram, that's the service data unit. But on layer 4, it's actually the protocol data unit. So this can get kind of tricky. And this gets, once again, the terms PDU and SDU, they're really more part of the OSI layer 7 model. But this terminology also applies to the 5-layer internet model that vendors use. The thing that I want you to understand is that you have this inside here, and I want you to notice how the shading is different. I have like cross shading here, and then I have slanted shading here, and then I have slanted in the other direction here. And when I pull them all together, what I get, if I put all this together, is this image here. This would be solid, this would be hashed, this would be slanted this way, this would be slanted that way. You're looking at the transport header, the internet header or network header, the NIC MAC address header, and then the physical header if possible, right? So you have signaling headers. What your author doesn't include on this end are all of the embedded CRCs. So on the outermost side, you have a frame CRC, a packet CRC, datagram CRC, and so on. So I want you to understand that when you collapse this diagram down, you have a single unit, and what you really see are all these headers. If you bring this header down, bring this header down, bring this header down, that's what we're talking about right here. Now I know I've kind of talked through this with you. The graphics aren't ideal. I have to come up with like an animated version of this with some computer graphics. Don't you think it would be easier to understand maybe? But I'd like to pause and ask if anybody has any questions about this idea of encapsulation. Encapsulation is when you're putting the layer PDUs and bundling them inside each layer as you move down, right? And once again, on the other side, when the other computer is getting that email message from the server, you have a physical connection between the switch on your area and that email server, and the frames are relayed to the switch across routers so there's switch to switch to switch and router to, we'll talk about switches and routers shortly, but you have this physical layer, and then you have a data link layer with the MAC address on the local area network, right? And that frame is unloaded, the SDU is removed, the payload is removed. That payload is called a packet. It's passed up to layer 3. That's where it's analyzed. We look at the sending and receiving addresses, and it says, oh, okay, this originating computer is from, and here's the destination. Oh, it's going to computer 2, and see that packet's going to match the address for the 2, the network address on this 2 of the address send and receive. Think of it as a box that you'd send in the postal service. It's going to match the address for the computer here, the network address for this computer. That payload's going to be unpacked. It's called a datagram as it's passed up to layer 4. Before it's passed up to layer 4, we check the CRC. Did it all make it? Are all the bits and bytes together? Are they in the right sequence, right? Gets up to the transport layer. So what am I saying? It starts up here and works down here on the sending side, and on the receiving side, it starts on this layer and it unpacks all the way up. Does anyone have any question about the terminology we used? Does everyone understand that a proper protocol data unit, it has a header, it has a tail or CRC on the end, and it has something called a payload in the middle. It's what you deliver, right? It's what's delivered. It's the contents of the inside of the digital box, basically. If you read through the text and the explanation, it should make sense. So I explained it visually, but if you read it and look at the diagram and read as you go, it should help, okay? Each of those containers is like a digital capsule, and that's where we get the term encapsulation. So encapsulation is this process where all of these packages are folded inside each other and then sent out across the wire. Can somebody say something so I know you're still with us?
Still here.
Still with you.
I'm here.
We're here.
Okay, very good. All right, what I'd like to talk about next is this idea of network addresses. So again, I ended up revising this study guide, and we kind of work around all of this. How many of you remember ands, ors, and nots from computer architecture? Do we have any? We have any fans in the
I
audience?
do.
Okay, good. Okay, so one of the things we want to understand is how the ones and zeros are used with Boolean operators so that the addresses work. Let's repeat that. On a very basic level, we want to understand when we have a network address, how are Boolean operators and the subnet mask used with that network address so that a computer knows where it's being sent and where it belongs. When you're on a network, you belong, when a client or device or system is connected to a network, it's one of hundreds or thousands of other devices, and each one has to have a unique network address. So it's really important for everyone to have a unique network address. That's called the client address. But in order to route the data packets and frames correctly, the computer needs to understand which network it's a part of. So as the digital communication process and digital networking process begins, there are these steps that a computer takes to understand, okay, who am I? What's my address, my unique address? And what neighborhood am I a part of? What network am I a part of? What network neighborhood am I a part of? And basically, yeah, we'll get into the private and public thing later. So if we have a network address, let's see. Let's say we have a network address, and I'm going to look at my own network address in just a minute. But let's say we have two devices on two networks, And one of them has a network ID of 146.226.0.0, and it has a subnet mask of 255.255.255.0. That's a /24. Well, what the heck are we talking about? In here on your network internet settings, if I go into, let's see. If I go into my Wi-Fi connection right now, and I look at my details, I'm sitting on a network address of 192.168.1.115. And what technology folks had to do some time ago is they had to find a practical way of relating the ones and zeros in a network address into decimal numbers, because it's really hard for people to look at decimal numbers. And then they have this added feature called the subnet mask, and you'll notice it's 255.255.255.0. And what you're going to find out is that this address for my wireless card was automatically assigned by a system called the DHCP server, and that automatic address was given to my laptop, to my wireless card for temporary use, and it also gave this subnet mask. Now, what that subnet mask does is it allows us to understand what's the client and what's the network. So in simple terms, these two pieces of information allow a computer to quickly calculate, okay, I know what my individual unique address is as a client. Now, what network do I belong to? So let's give you a quick example of what we're talking about. Here, what a 255 is in decimal terms is actually 8 ones. Does anyone remember this from last semester? Does anyone remember that 255 is actually equal to 8 ones?
Yeah.
Okay. So if I have a subnet mask that's 255.255.255.0, what I really have are 8 ones, 8 ones, 8 ones, and 8 zeros. If I have, and we call that a /24, this is called CIDR notation. It means a little more than just the number of ones, but basically it's a slash with a number of ones. So this decimal, it's called dotted decimal notation, is a easy way for us to work with because we're used to decimal numbers. So we say, okay, my subnet mask is 255.255.255.0. What that means in binary terms is that I have 8 ones followed by 8 ones followed by 8 ones. That's 24 ones. And I have 8 zeros. But that's different. It's totally different from a device that has a subnet mask with a /16. It's a 255.255.0.0. What that means is that I have 8 ones followed by 8 ones followed by 8 zeros followed by 8 zeros. And what your computer does is it takes the network address on your device and it uses and it uses the AND operator, the Boolean operator, and combines the subnet mask with your network address. Now, why does it do that? It allows you, when it does this, it allows the computer to say, okay, now I know where the network is, and now I know what my individual address is. So the best way to explain this to you is to give you an example. Let's say that I have a computer that has an address that was automatically assigned, and it's 172.16.0.23. Now I want you to notice how I'm saying this. I use the term dot instead of period. If you want to be considered a noob or an uninitiated techie, use the term period. I mean, that's what civilians do. That's what normal consumers do. When they call in tech support says, yes, I need your help today to fix your network problem. I need you to read off your IP address. And they may ask you to look it up like we just did on this screen. Or they may ask you to do something like this with a command prompt where you type in ipconfig. And it gives you that information for your wireless card, ipconfig. And my wireless card has an IP address of 192.16.1.115. For non-technical people, they say period. Don't do that. Use the word dot, right? And so let's go back to this example. Let's pretend we have 172.16.0.23 and I have a subnet mask of a /16, right? And then we'll take this second example of 172.16.214.105 and we're going to apply a subnet mask, a 24-bit subnet mask to it. Well, what you're going to notice is that here, wherever you have ones, when you apply the AND, it keeps these numbers. And whenever the zeros appear, it loses those numbers. So the network address is 172.16.0.0. When these ones are applied with the AND, the first part of the network address is 172. When these ones are applied with an AND to the second octet, so this second cluster of numbers is called an octet because there's 8 bits. 8 means, octet means 8. This part of the network address, you know that it's part of the network address. So the network that it belongs to is 172.16.0.0. Everywhere you have zeros, when you AND it with zeros, you could have ones and zeros here, but if you're ANDing it with all zeros, if you remember from your computer architecture days, all the values have to be a 1 in order for the number to be preserved. If there's a single 0 in there, then basically the outcome is a 0. So when this computer is looking to see, okay, what network am I a part of? It's going to say, because of my subnet mask, I'm in the 172.16.0.0 network. And my client ID is 23. So the subnet mask shows you where the network identity can be read and where the individual client address can be read. This is the network address or the neighborhood, and this is the individual location in the neighborhood. Let's repeat that again. This is the number you need to find the network neighborhood, and this is the number you need to find the individual device or system in that neighborhood, right? It's kind of like how your mailing address has a street address and a city address. You got to get in the right neighborhood, and then you have to know which house in that neighborhood. So this tells the computer which network neighborhood I'm a part of, and this part of the address tells you, once you get there, I'm going to house number 23. I'm going to device number 23. That's what our subnet mask does for us. If I take that same idea and I apply it to this second example here, my network address here is a little different. I have a 172.16.214.105 network address, and I have a /24 subnet mask. So the computer says, okay, I'm going to apply the logic operator, the Boolean operator, and to this number and this number and this number and this number. And when I run out of ones, when it becomes all zeros, I just drop this and replace it with 0. So my network address is 172.168.214.0. And what's the client address? Well, for this device or system, my address is 105. So let me say that again. My network neighborhood is 172.168.214, and the house address or device address is 105. So what are we saying? The subnet mask provides a boundary where we can chop, and everything to the left side where the ones are is your network address. Everything to the right side where the zeros are is your client or house address.
The screen stopped sharing.
Yeah, the screen stopped sharing.
The screen stopped sharing. I'm sorry. Thank you for telling me this. Okay, can everybody see my screen?
Yeah.
Okay. So the subnet mask where the ones are tells you which numbers are the network address used for the network address, and where all the zeros are, all the numbers in that IP network address identify which house or which device you're from. Okay. So what's interesting is that hackers understand how this works. So I have a question for you. This has to do with zip codes. Let's change this up a little bit. I want to give you 2 examples. Can everybody see my 2 zip codes?
Yeah.
Yes.
So let's pretend I'm addressing an envelope. Okay? Let's pretend that we're using a subnet mask for the Postal Service instead of networking, digital networking. And let's pretend that the subnet mask in this case includes this many numbers, right? And then let's say the subnet mask. Well, first of all, let me ask. Let's just go back a second. Are these the same neighborhoods, the same towns? If you were working with packages and envelopes and you were working with the US mail, the Postal Service, do these 2 zip codes represent the same city or town? What's the likelihood that they would be the same? Let's ask the question a little differently. What's the likelihood that these 2 would be the exact same town or the exact same city? The same neighborhood. Let's make it simpler. Do these 2 zip codes represent the same neighborhood? Yes or no?
Probably yes.
I would say no, but it'll be someplace in the same state.
Yeah, I would agree with the second individual. So it's probably in the same state. And how do you know that? Well, that's because the first 3 numbers match, right? But is it the same neighborhood in the same state? Oh no, not at all, right? So a similar thing happens when you're using a subnet mask. Your computer needs to instantly identify what neighborhood am I in, and then it knows what to look at for neighbors, right? So your computer makes this snap decision about what neighborhood it's in, and then it knows what neighbors it's allowed to look at. The one computer can say, let's say I had a smaller subnet mask on this one, and this was my network identity. And then let's say I had a larger subnet mask on this one, and this is my network identity. Are those the same network identities? Well, are they related network identities? Everybody's shy. Let's do it this way.
Yeah.
Are these the exact same identical networks? Are these the exact same identical neighborhoods?
No.
No, they're not. Because this is 2900 and this is 2909, and that means they're identical. So let's pretend that the subnet mask here says, hey, you have to look at 4 numbers to determine what neighborhood you're in. This device is going to look and say, that's not part of my neighborhood. Now, they could be on the same wireless. They could be on the same local network with the same Ethernet. But this device is going to say, I'm looking for 2909s. I'm looking for other devices, other systems in my same neighborhood. And it looks and sees this device and says, that's not a match. 2900 doesn't match 2909. But let's pretend for a second that on this device, the one on the top, the way the subnet mask works is a little different. And I know I'm fishing here, but let's say the device on the top says, I'm looking at the first 3 numbers to determine who my neighbors are, my neighborhood. I want to know who my neighbors are in my neighborhood, and I want to know what neighborhood I'm a part of. And the top device says, hey, by the subnet mask, I'm paying attention to the first 3 numbers. I don't care about 4 numbers. When it looks out on the wireless, it's going to see this instead. When you're sitting on this device, when it's looking out on the network, the physical network, it sees this other device sitting out here. Does it think that this is part of the same network?
Yeah.
It does.
Yes.
It does. So if I take 4 digits down here, I don't have a match. I have 2900 versus 2909. So this device is looking out on the wireless and it says, hey, I can't pay any attention to this. This top device here, this top system or laptop or tablet or cell phone or whatever, this thing isn't in my neighborhood. It's not a peer. It's not a neighbor of mine. So I'm not going to pay any attention to what it's saying or transmitting. The top device uses a different subnet mask. And the subnet mask on the top device says, hey, I only care about the first 3 numbers. Who's in my neighborhood? Who's a potential neighbor of mine? It looks down below and it sees the lower device or lower system or laptop or tablet or cell phone. And it thinks what? Oh, this device is in my network neighborhood. This device is a neighbor of mine. I can communicate with it. What am I saying? I'm saying that hackers know how to manipulate the subnet masks so that they can view more than they're supposed to. That's one thing that's significant about this concept of subnet masks on a binary or bit level that's important to understand. In plain terms, what you need to know is that the subnet masks have to be the same and the network addresses have to be the same if 2 devices are going to communicate properly, like they're supposed to. But if you're a hacker, you can change your subnet mask. You can make it different than it's automatically assigned so that you can see more of a network neighborhood and see more clients in that network then you're supposed to be allowed. Ordinarily, the subnet mask and the address are automatically assigned so that you don't ever think about this or know about this. But it's very easy to assign your own network address. All you do on here, if I wanted to change my network address, I could go into properties and double click on TCP/IP. And instead of using an IP address automatically, let's see, let's make sure I note what that address is. So I'm going to look at the details here. I'm going to take a screenshot of this because I don't want to forget this. My current network address is 192.168.1.115. And I have an automatically assigned 24-bit or /24 subnet mask, which means that 115 is my client address. And I'm sitting on the neighborhood that's 192.168.1.0. That's my network neighborhood. And if I'm an evil person, I'm going to go ahead and take a snapshot of this. So let's open a new paint window, and I just want to know what this is. I could change my address. I could change my subnet mask. If I wanted to, I could go in here and manually assign, whoops, I could manually assign my own address and not follow the automatic assignment. And I could say, okay, I'm going to make this 192.168.1.204. And my subnet mask is going to be 255.255.0.0. And my default gateway, we're going to show you how to calculate a gateway in a minute. A little later in the next modules. It's 192.168.0.1. So if I make this manual change, now I'm not just looking at anything that's 192.168.1. I'm looking at any device that has 192.168.1, .2, .3, .4, .5, all the way up to 255, right? My network device has now become a tool for hacking because I've manually manipulated or intentionally changed my subnet mask so that I'm looking at all of the 192s. I don't care what else the rest of it is. I just want to see as much network out there as possible. Or I'm looking at 192.168s. So if there are any other networks in the neighborhood that are connected, and they're supposed to be separate private networks, I can get in there and I can look and see what's going on. So one of the things that I want you to understand is this relationship between the length of the subnet mask and how that's used to determine the network address from a given network address. And I get different results. If I have a subnet mask of /16, this device can see this one. This device cannot see this one because this device is looking for 172.16.214 addresses on the wire or in the wireless. And when it looks, it sees 172.16.0 and it says, well, that's not a 214, so I can't look at it. I'm client identity number 105 in the 172.16.214 network because my subnet mask chops this off right here. As I'm looking at this other client that's sitting on the network, on the physical network, on the data link layer, on the local area network, this device looks like it doesn't belong to my network. So this machine says I can't see this one. This machine says, okay, my subnet mask only cares about 172.16 because my subnet mask chops off right here. My client address is 0.23 or 23. What can I see? Oh, here's this other client, this other system, this other device on the 172.16 network, and its client ID is 214.105. So the subnet mask helps us determine what network neighborhood the device or system lives in and what part of that address is actually unique for the client. Like the building address on the street. This is the town and this is the building address on the street. This is the town and this is the building address of the street. These are two totally different networks. But if a hacker knows what they're doing, they can change a few things manually, and then all of a sudden, you have computers that can see things they're not supposed to. So I know that's a lot to unpack in a single day, but the best way to do this is to read the book and to read the study guide from start to finish, now that we've got the graphics straightened out and the sequence straightened out. And then tomorrow, what we're going to do is send you a link to get started in the Net Academy as a part of your solution. So for your solution, you're going to log into a website called netacad.com. If you haven't already done this yet, you should have received an email. You would click on that email link that you received. You would log in and establish a password. Once you've established a password with your UVI email address, you're able to log in and then do what you need to do for your solution. Are there any questions about getting started for your Module 1 solution? Is there anyone in the class now that has not received an email from cisco.com or the netacademy.com? Hello?
I think I received it. I just have to go look for it.
Yeah, me too.
Right. So your screen is going to look a little differently than mine, but when you come into your profile, you should see a course called Introduction to Packet Tracer, Spring 2021. You're going to go ahead and click to launch the course. It's going to bring you into some resources, and the resources will explain to you what Packet Tracer is, and it'll explain to you, right? So here's the introduction, and see here it says first time in the course, student support and resources, and it would be good for you to click first time in this course, but after you go ahead and review this information, student support and resources, download and install the latest version of Packet Tracer. This is what you want to do for your solution. This is going to show you how to go ahead and do this. Manually speaking, it's going to tell you to go to resources and then Packet Tracer, or download Packet Tracer. And then you're going to follow along here, and it's all basically self-paced and laid out for you. There's a video And you just follow the instructions, right? Download the PKA file and instructions. You're going to want the latest version, version 6, and you're going to want the one in English. This is a certificate that you use that tells the software that you're authorized to use that software. Are there any questions
Yeah.
about,
Where are you trying to go?
we're going to go to the,
TSA? No, TSA is over there.
the course details, right? And the assignments. When you go to the course details, you can launch the course. And then you can read the information, Introduction to Packet Tracer. You're going to click on any image to start. This other window is going to open up. Some of this is text-based information and some of it's video. So you're going to read here and then click to advance. After you finish getting some basic information about an overview of Packet Tracer and how it works, when you click again, it'll show you how to install. So here's an overview of Packet Tracer and what it does, video. And then you click here and it shows you what to do to download and install. Okay. When you're finished with the installation process, you're going to start Packet Tracer
Hey, there's a bathroom right there.
and take a screenshot of your installed Packet Tracer. Again, there will be more details. It'll be a step-by-step you can follow, but that's what we're going to do for your solution is get set up with Packet Tracer. Are there any questions about your initial screens and expectations when you get into Net Academy?
None so far.
Does anyone have any questions about the material we covered today before we close?
I don't have questions.
Okay.
Hello?
Was there a
Hello.
question?
So you said we're supposed to download a program by Wednesday. What's the name of that program?
It's called Packet Tracer.
Can you
I'll
put a
have-
link on Blackboard for that?
Yes, I will. I will have a link out there for the assignment for you to follow.
All right. Because I tried to download it, but I didn't know the name.
Yeah, it's a Packet Tracer, but you do it from inside Net Academy after
Hello?
you've gotten into the screen.
All right.
Okay.